If you're here to learn about the fundamentals of science, then welcome to Genetimix. My name is Tim, and on this channel we cover science communication, critical thinking, and a wee bit of genetics. We'll start with a quick definition. Science is the systematic study of the structure and behaviour of the physical and natural world through observation, experimentation, and the testing of theories against the evidence obtained. What I'm going to give you right up front is the key takeaways I want you to have about science. I realise this is probably some kind of mortal sin against the YouTube algorithm. We will then dive into a lot more detail and revisit them once more at the end. First off, all science is provisional and contingent. These are the best available evidence and explanations we have right now, but these may be updated or even superseded in the future. Nothing is proven in science. Does that mean we should somehow lack confidence in the findings of science? No, because what we do have is well-substantiated, evidence-based explanations of aspects of the natural world that are supported by repeated observation and experimentation and can be used to make predictions. This is the definition of a scientific theory, the highest possible accolade that can be accorded to a scientific explanation. In other words, science is useful. Even though we might not know all the details, what we do know allows us to make useful predictions, and these form the basis of all of our technology, technology itself being defined as the application of scientific knowledge for practical purposes. All our technology comes from science: food, transport, energy, medicine, agriculture, manufacturing, engineering, innovation, YouTube, your phone, all of it. And anyone who uses the phrase, "it's only a theory," about a scientific theory, either A, does not understand what a scientific theory is, or B, is deliberately trying to mislead their audience. Science aims to be as rigorous, open, unbiased, and collaborative as possible. It requires publication of articles in journals that are peer-reviewed. The methods and data are required to be published, and the study should be testable, repeatable, and falsifiable. In other words, other scientists should be able to reproduce exactly what you did. This process is not always perfect, but again, we do our best, and it's been pretty damn effective so far. Unfortunately, quite a bit of scientific publication is hidden behind paywalls, economic reality biting here. But college or university students and staff in particular will still be able to access all of it via their academic institution. Science is big. I mean, really, really big. There are at least a couple of hundred fields of scientific study, and that's at a high level, way more if you want to get fine-grained. Recent estimates place the number of scientific papers published each year at between 2.5 and 2.8 million. We've learned a monstrously large amount about the natural world and are learning more and more every single day. This does mean that nobody knows all of science or ever will. Again, back to the previous point, it's a massive collaborative effort. Science is not a belief system or a worldview. Scientists do not blindly follow teachings or authority figures. The only thing that scientists do follow is repeated observations and evidence, and falsifiable, prediction-making, evidence-based explanations. And even that is only done in a background of systematic, peer-reviewed skepticism. In summary then, science works. In the rest of this video, I'm going to take a look at some of the assumptions that underpin science and delve a bit more into the details of the scientific method and how scientists go about doing science. Science starts with observation of the natural world, our planet and everything on it, and beyond that, our solar system, our galaxy, and our universe. There is a philosophical worldview or stance called naturalism, usually referred to as metaphysical or philosophical naturalism, which maintains that only natural laws and forces, as opposed to supernatural ones, say, operate in the universe. So the first assumption that underpins science is what we call methodological naturalism, which is that naturalism should be assumed in one's working methods. Science makes this assumption for largely practical reasons, as it appears to be impossible for us to observe, detect or measure supernatural influences, so we just can't test these. As part of this, we assume that there is an objective reality shared by all rational observers. We are all seeing and experiencing the same reality, and that this objective reality is governed by natural laws. In other words, the physical world is orderly and comprehensible. We further assume that this reality can be discovered by means of systematic observation and experimentation. So we start by observing and measuring what we currently see. However, a lot of science is dedicated to studying how we got to this point, in other words, investigating what happened in the past. In this sense, scientists act very much like detectives, piecing together what is most likely to have happened in the past from whatever evidence we have been able to gather at the scene. So we assume that nature has uniformity of laws, i.e. these are unchanging over time. This assumption is required for us to be able to extrapolate from the known to the unknown, and to be able to draw general conclusions from a finite number of observations. We make the exact same kind of assumptions in forensics and law. We assume that experimenters won't be significantly biased by their presumptions. Remaining unbiased and open to any and all possible explanations is one of the hardest things to do in science. We assume that random sampling is representative of an entire population, and we also assume that scientists will perform experiments satisfactorily and without deliberate or unintentional mistakes that will influence the results. The scientific method is a set of tools and guidelines that scientists use to objectively establish scientific facts through testing and experimentation. The scientific method consists of 7 basic steps, usually summarized as question, research, hypothesis, experiment, data analysis, conclusion, and communication. These are not set in stone. This is not a dogma. There are some scientific fields where directly observable experiments can be difficult to perform. Quantum theory leaps to mind. Yet we are still able to make scientific progress investigating these fields. The steps of the scientific method are usually shown as a cycle, and as you progress in science, you keep repeating this cycle over and over. Each iteration of the cycle builds on the last, and each iteration adds to the body of scientific knowledge that we have. The first step is to define the scientific question we wish to answer. Next, we will gather background information and resources to help us answer this question. It's likely that we'll be starting with the conclusions drawn from the last round of investigation. The next step is to create a testable, explanatory hypothesis with inductive reasoning. The use of the word theory outside of the scientific realm more closely matches a scientific hypothesis, which is a supposition or proposed explanation made on the basis of limited evidence as a starting point for further investigation. For a hypothesis to graduate to become part of a theory requires scientific evidence. Next, we will move on to experimenting, testing the hypothesis by performing an experiment and collecting data in a reproducible manner. A proposition is a statement that can be either true or false, and evidence is something that supports a proposition, usually taken as an indication that the proposition is true. Empirical evidence is evidence obtained through sense experience or experimental procedure. It is of central importance to the sciences and obviously plays a role in various other fields like epistemology and law. Empirical evidence requires the use of our senses, and these are not always all that reliable. For example, we consist of trillions of tiny cells, each of which is made up of trillions of even tinier atoms. Because our senses and even our imagination struggle with all of this, we've come up with methods to help us make these observations, and other methods to help us build trust in the measurements and observations we make. Scientific evidence is empirical evidence which confirms or disconfirms a scientific hypothesis and arbitrates between competing hypotheses. The strength of the scientific evidence is based on statistical analysis and the strength of the scientific controls. Falsifiable is a statement, theory, or hypothesis that can be tested by observation or experiment in a way that could potentially prove it false. For a claim to be falsifiable, it must make specific predictions that can be measured to determine if they are true or false. Falsifiability is crucial in science because it allows scientists to modify or discard hypotheses or theories that contradict empirical evidence, strengthening the scientific process. A claim that cannot be proven false is not falsifiable and is generally considered unscientific. Next, we move on to data analysis, where we will analyze our data, including establishing statistical confidence in our results. If we've designed our experiment correctly, we will have isolated variables and created a null hypothesis. In science, to isolate a variable means to ensure that only that independent variable is changed during an experiment, while all other factors, which we call control variables, are kept constant. This practice allows researchers to determine if the changes observed were caused by the specific manipulation of the independent variable, thereby establishing a clear cause and effect relationship, and to help clearly distinguish between correlation and causation. This is also why scientists prefer to perform experiments in controlled environments, such as a laboratory, although this is not always possible for some fields of science, such as astrophysics. A null hypothesis is a statement that there is no significant relationship or effect between two variables, and that any observed differences are due to random chance. It is the default position in statistical testing that researchers try to disprove by collecting evidence to support the target hypothesis of this iteration. The null hypothesis assumes a lack of effect until enough statistical evidence proves otherwise, similar to how a legal trial presumes a defendant is innocent until proven guilty. The null hypothesis is assumed true. The test does not try to prove the null hypothesis, instead it tries to find evidence to prove it wrong. P-value is the probability of obtaining results at least as extreme as the observed data, assuming the null hypothesis is true. It measures the strength of evidence against the null hypothesis. A small p-value, typically below 0.05, indicates the data are unlikely to have occurred by chance, suggesting strong evidence for our target hypothesis. Our next step is the conclusion, where we will interpret the data and draw conclusions that serve as a starting point for a new hypothesis. And here we introduce the concept of a scientific fact. We can define a fact as something that is known to have happened or to exist, especially something for which evidence exists or about which there is information. A scientific fact is the result of a repeatable, careful observation or measurement by experimentation or other means, and requires empirical evidence. A scientific fact implies having scientific knowledge. Knowledge is defined in philosophy as a justified true belief, or in layman's terms, as the sum of what is known, an awareness of facts, a familiarity with individuals and situations, or a practical skill. Scientific knowledge, again, has a more rigorous definition. It also needs to be testable, refutable, and falsifiable. The next step in the scientific method is communication, where the results are usually published. Most science is published by the peer review process, where the methods, results, and conclusions of the experiments are rigorously checked by other qualified scientists. The peer review process involves the publishing of the actual data found during the experiment. The results need to be available and accessible, with the aim that other scientists will be able to repeat the same experiments and get equivalent results. As mentioned earlier, the results are usually published with a statistical confidence figure. The peer review process is transparent and makes every effort to eliminate bias and mistakes. It isn't perfect, and occasionally papers will slip through that will later be discovered to contain errors or even be fraudulent. These papers are retracted. The final step is to retest. I've mentioned a few times that scientific findings need to be repeatable. This retesting is frequently done by other scientists in another iteration of the scientific method, with its own separate publication at the end. I will also just point out here the similarity between the scientific method and my lighter weight iris approach to critical thinking. These similarities are not a coincidence. I would also briefly like to mention the scientific consensus. This is the collective judgment, position, and opinion of the majority of scientists in a specific field, based on the overwhelming weight of evidence. It is not a vote, but instead the result of a rigorous process of observation, experimentation and peer review, where many independent studies point to similar conclusions. This consensus represents the most robust and reliable understanding at a given time and is crucial for informed decision-making. Consensus is not always 100%. It doesn't mean that every single scientist agrees on every detail, but rather that there is a general agreement on the core conclusions. Like all science, the scientific consensus is provisional and contingent. It can evolve over time as new evidence emerges and scientific understanding advances. And I would further class the scientific consensus as apolitical. It is the product of a painstaking evidence-based process. It's not opinion, it's not a conspiracy, there's no hidden agenda. As mentioned up top, science is big. For the last part of this talk, we're going to take a brief tour of just how many fields of science there are. I've put together a mind map containing the main areas of science and some of the research fields within each of these. Science is basically divided up into formal sciences, up here, natural sciences, and social sciences, with natural sciences being broken up into life science, which is basically biology, and physical science, which is physics, chemistry, earth science, and astronomy. The boundaries between a lot of these fields can sometimes be more than a little blurry, which is why some of them appear in multiple places on this mind map. I have additionally added some applied fields to biology simply because this is where I'll likely be spending most of my time and attention on this channel. There are more than 200 fields of science on this mind map, and this is without many composite fields being included. For example, we have microbiology and genetics, but not microbial genetics. If your particular research field is not here, please let me know in the comments and I will add it to the map. So let's have a very brief tour. We will start, of course, with the formal sciences, which include things like logic, mathematics, statistics, data science, and computer science is also up here as well. Next up, of course, is physics, where we've got the fields of quantum mechanics, electromagnetism, relativity, thermodynamics, and over here we've got classical mechanics. And down here we've got what I've loosely termed interdisciplinary physics, which includes all of the bits of physics that overlap very heavily with other fields of science. Up at the top left we have astronomy, which includes astrophysics, again major overlaps with physics, some various techniques used in astronomy, and then we've got crossovers between astrobiology and astrochemistry. Moving down to earth science, we've got strong overlaps with planetary science and astronomy, atmospheric science, oceanography, geology, geography, including again interesting overlaps between other scientific fields such as paleontology, geophysics, biogeography. Moving down to chemistry, we've got physical chemistry, inorganic chemistry, organic chemistry, and what I've loosely termed other chemistry, other bits and bobs. And I've drawn here some of the significant overlaps between chemistry and biology, particularly things like molecular biology, biochemistry, and abiogenesis, the study of how life got started in the first place. And wrapping up our tour with a brief look at biology, where we've got things like biomedical, what I've loosely grouped together as multicellular biology, microbiology, and then some cross-discipline biology, both within biology itself, including core concepts like cell biology, genetics, and bioinformatics, along with crossovers like biochemistry, astrobiology, paleontology, which appears here as well. Anyway, I hope this very brief tour has provided a little insight into just how much there is to science. And to hook back round to where I started this talk, I hope the extra detail provided helps to reinforce the original take-home messages. So to reiterate by way of summary, science is provisional and contingent. It's useful. It aims to be rigorous, unbiased, open and collaborative. It's big. It's not a belief system or worldview, and science works. Science, as it is practiced today, is a collaborative, transparent and rigorous process with the aim of gaining an increasingly better understanding of the world around us. In my view, the assumptions and methods that underpin science have been emphatically justified by the overwhelming success of science in meeting its goals so far. And there's still so much more to be discovered and understood. And that wraps us up for today. Don't forget to like, subscribe and comment. My social media feeds and Patreon are in the description below. Remember, science is amazing. Thanks for joining me, and I'll see you again soon.